Everyone, welcome back. So let's talk in more detail about the steady flow process. We saw this last time with the water condensing on a pipe, but now let's actually develop this in more detail. So what is a steady flow process? It's a process which is steady. So you have fluid that's flowing through your control volume at a steady rate. Now, most things that are developing power that we deal with operate in steady state a lot of the time. Like nothing does it forever. Like even a nuclear power plant, which is going for months or days at a time, eventually has to be either you have to change states, you have to do maintenance on it, and when you do that, you're going to have some sort of startup or shutdown process that is not a steady state. But for much of the time, and much of the time is what we care about, it will be going steadily. So because of that, we can develop the math. Now, under steady flow conditions, I'm going to know two things. One, the mass of my control volume is going to be constant. And two, the energy in my control volume is going to be constant. That means the energy going out and the energy going in is the same, and the mass going out and the mass going in is the same. But it doesn't have to have a single outlet and inlet, though that is wonderful and many devices do. It can have multiple inlets, and these rules would still be the same. The mass flow going in would be equal to the mass flow going out added together. And the energy going in, which is the mass flow times the enthalpy, would be equal to my energy going out added together. Now, in these two little pictures right here, I didn't show any sort of work or heat transfer, and real-world systems will have both of those. So let's look at one. In this case, I have a water heater. It's in steady operation. So, first thing I know is I only have one inlet and one outlet, so my mass flow in is going to be equal to my mass flow at the outlet. Pretty easy. Then how about energy? Well, we know that the electric hot water heater is powered by this electric heating element. That is what provides the heat. So that has to be equal to the change in energy from the cold water going in to the hot water going out. It is changing the heat there, as well as equal to the heat going out. So I have to take into account both of those. There is a change in enthalpy from my inlet to my outlet, as well as heat leaving through radiation, because your hot water heater is always going to lose heat. That's why you probably should insulate if you want to help it not do that, so you can reduce your costs. Now, since it's a steady flow system, we know that the change in energy in my control volume is zero. And so that means the energy going into my system is equal to the energy going out of my system. It might look something like this. Okay, this is the full energy balance. I'm writing out everything except for the theta term. I haven't fully written that out yet. But you know what? Why not? And this is a massive equation. So let's look at all these terms here. I have heat in, work in. I've got heat out, work out. I have a mass flow rate in. I have a mass flow rate out. And then I have an enthalpy, a kinetic energy, and a potential energy both going in and going out. Whew. There is a lot of stuff here. Now for our situation, it's not too terribly bad. First off, we don't have any heat going in. We don't have any work going out. Okay, that makes things a little bit easier. Other things to think about is for this hot water heater, the change in potential energy is negligible. It's very small. You're going from the top of a hot water heater to the bottom, and in most cases, you have your cold water and hot water supply coming out of the top. So they're both at the same point. So that's equal to 0 too. Since we have the same mass flow going in and out, and usually the pipes are the same size, we're not going to have really any change in kinetic energy either. So we can say that those are going to be going to 0 as well because they're going to be the same on both sides. So with all of that, this term has really simplified a lot. And I'm going to just mark through the kinetic energy and potential energy because technically they would have a value. It's just that the change would be 0. There we go. So wouldn't it be nice if we could simplify this? Well, we can. So first off, we can just bring all these terms together, which looks a little bit nicer. We're collecting terms. But this still isn't as simple as it could be because if we remember that our kinetic and potential energy changes are negligible and that we have a single inlet and outlet, which means the mass flow rates are the same, I can simplify it all the way down to here. Okay? All the way down to here. Where in this case, lowercase q would be equal to my q out over my mass flow rate, and lowercase w would be equal to my work in over the mass flow rate. So I can take those crazy equations and I can simplify it down to here. My change in enthalpy from one place to another will be equal to the heat going out minus my work. And sign conventions do matter there, which is why we can do that. Cool. I think that's it for this time. Yep. So we're going on to an example. So I'll do that next time. Have a good day. Bye-bye.